Welcome back. This is Fundamentals of Micro and Nanofabrication. This lecture is under the module of additive processing. We were discussing atomic layer deposition. We looked at the basics of atomic layer deposition, what is its main USP, the mechanism behind layer by layer growth. In this lecture, we shall get into a little more details, look at deposition window, look at some nucleation aspects, look at advanced features such as plasma enhanced ALD, etc. Let's get started. So, one of the things we have not touched on till now, one of the parameters that you control during the deposition that we have not touched on is the substrate temperature. So, substrate temperature actually has a huge effect on ALD, and it's also something that must be optimized for a recipe. So, what are the various things that can happen? So, if you look at this figure, you want to do ALD in a window where the growth is self-limiting, so somewhere in the middle. And in the self-limiting growth, by and large, the growth per cycle is independent of substrate temperature. So, that is where you want your ALD to be in. But of course, when you start a new recipe or you are designing a new recipe, you do not know what that window is. Suppose you are, say, playing with a new precursor, so you do not know where that window of that precursor is. So, you must run some test and optimization cycles to actually extract what this window is. So, what might happen when you do the ALD growth at various substrate temperatures is you can see some non-linearities that will happen at lower temperatures and at higher temperatures. So, two things can happen at a lower temperature. One is that your precursor tends to condense on the cold substrate, right. So, you are reducing the temperature, the precursor is cold, and the volatile material just condenses on the substrate. Imagine this is what would happen if you cool the wafer and you are letting in water, right. So, if you are cooling the wafer and you are letting in water, there is a possibility the water will just condense on top and form a film, just like mist condenses in the winter morning on top of leaves, right. So, if that happens, then this is not adsorbed or chemisorbed water on the surface, right. This is just condensed water on the surface. This can be arbitrarily thick, and if it is arbitrarily thick, you would have so much precursor that you would, when you send the component A, which reacts with water, you would form a lot of material, but that would be a CVD-like reaction, right, because it's not a self-limiting reaction, it is an unlimited reaction. So, your growth per cycle will be larger, you will actually get more growth, but that growth would be non-uniform, as we discussed in the previous lecture, and that is not good. You want it in the ALD window. The other thing that can happen at lower temperature is you have that the precursor just does not react. So, the whole ALD assumes that the component A reacts with component B, but that requires a certain amount of reaction rate, and reaction rates are often limited by temperature, and at very low temperatures the two components might not react. So, in that case you would get a lower growth than what you assume, and this is also not good because this is also not the self-limiting case, because the whole point is you form this self-limiting layer of component A reacting with B to form a layer of deposited material. If that layer is not reacting, then the growth is not self-limiting. At higher temperatures also two things can happen. One uncontrolled growth could be that the precursor sort of decomposes on its own. So, ALD assumes that precursor A reacts with precursor B to form the material that you want, but precursor A alone is unable to do anything, it cannot form the material. But any organic material or any chemical material will have some decomposition temperature. What if the temperature is so high that the material just decomposes into some nonsense constituents which may or may not even be the material you want to deposit? So, you will get some growth, but that growth will be very much like CVD, because this is, if you think about it, a pyrolysis reaction, right. So, if you flow silane and the temperature is 1000 degrees C, silane will break and form silicon, but that is not ALD. The other thing can happen at high temperature is that precursor starts desorbing. So, till now we have harped on the fact that this is a chemisorbed species, the desorption is minimal, it is a one-way reaction, but everything has a limit. If you heat the substrate enough, you may be able to provide enough energy to get over that chemisorption hump, and the material just desorbs, unreacts itself. And if that is the case, you do not have that self-limiting layer, you do not have the component B will come and have nothing to react with, and you will have a lower growth rate, but that would be an uncontrolled growth rate. It would be not repeatable, and it would not be consistent. So, it would be outside the ALD window. What you want to always do is keep your growth somewhere in the middle where things work as an ideal ALD should. Now, which of these two cases occurs really depends upon the precursor and the chemistry you are using. If I take an example of, for example, of diethyl zinc and water, which is reacts to form zinc oxide, it tends to show a ALD window of this type where there is incomplete reaction on the left hand side and there is desorption on the right hand side. On the other hand, tantalum oxide formed using tantalum ethoxide and water tends to have a very different looking ALD. So, once again you have the ALD window in the middle, but on the left you tend to have condensation, on the right you tend to have pyrolysis. So, different precursors do different things. The goal in every case, however, is to find this region of flat where you can do your reactions. Let us talk a little about our nucleation and growth. So, we discussed nucleation a lot in CVD. We shall not go into that much detail in ALD because it is not required, but there are certain non-idealities that occur that must be explored. So, let us take the simplest case. We assume that in ALD the thickness versus number of cycles will be a linear process, right. I showed you an example of TMA and water where it is exactly linear. So, that is this dotted line of equal nucleation, but sometimes materials or certain chemistries give you a slightly different form. They are linear at higher number of cycles. So, they are linear here and they are linear here, but they might have an enhanced growth initially or they might have a suppressed growth initially. So, what is the cause of this initial non-ideality? So, in cases where there is less nucleation, what might be happening is that the precursor does not stick to the surface. So, the surface energy is such that it does not form a nice contact angle, and the large contact angle means the precursor sort of sits in globules, not as a adsorbed film. So, if that actually happens, then you can imagine the growth rate will be lesser because their self-limiting film is not as widespread. At the same time, it could be a case where the precursor sticks to the material a little bit too well, and if it does that, it might just form a very low contact angle film on top of the substrate, and that might lead to more nucleation than you hope for. So, when I say less or more, I am basically comparing to the case of what is the contact angle of the precursor on top of the deposited film. So, once you have formed a little bit of deposited film, then in all those cases this contact angle will be the same, right. However, when the growth is starting, it is not seeing the deposited film, it is seeing the substrate. So, the contact angle of the substrate, the initial contact angle on the substrate might be different, and that is what explains these initial non-idealities. So, what can we do about it, or how do we sort of look at it? So, here are two examples, one of more nucleation and one of less nucleation. So, this is the same mass gain as a function of time curve that I showed you before. So, what the curve you have seen before is this orange one, right. This is the basic TMA reacting with water to form material, aluminum oxide. But if you try to do this reaction on titanium dioxide, it turns out that TMA has an enhanced sticking to the titanium dioxide surface. So, cycle 11, which is one of the initial cycles, the early cycles, you actually get more mass gain than what you bargain for. So, your mass gain is larger, and most of this difference is actually not in water. Water absorbs roughly the same, or the mass gain due to water is essentially the same. Most of the difference is because of the very different mass gain of the TMA. But as you keep doing the deposition for longer and longer, once you get to cycle 75, that difference goes away and you reach back to that steady state, right. So, initially you have enhanced growth, later you have the same growth rate. The other example is supposing you were trying to do titanium nitride deposition on silicon dioxide using this chemistry at 1000 degrees C. This is an example of less nucleation. So, if you look at the film thickness as a function of number of cycles, initially you would actually see almost nothing. So, you would think that there is no growth happening. But if you wait for some time, ultimately the nuclei form very slowly but surely, and then once you get a film of titanium nitride on there, from that point onwards you start nucleating normally and you see a linear growth. Alright, so these sort of non-idealities can occur. Here are some references that actually go into details of both these things. One of the ways you can solve nucleation and some other issues is to use plasma. So, this is the relatively new area of plasma enhanced ALD. Equipment to do this has just started becoming available commercially. So, the basic idea is fairly simple. Till now we are doing thermal ALD, which is that all the reaction rates and the mechanism and the chemisorption all assumes thermal energy, right. So, depending on the substrate temperature, things would either happen or not happen. But if you want to help things along, you can always add some energy through some other sources, and plasma is the common technique that we have done. So, just like plasma enhanced CVD allowed us to reduce the temperature and enhance the growth rates, similarly plasma enhanced ALD would also allow us to reduce the temperature even further and enhance growth rates. So, here an example. So, we are looking at growth of aluminum oxide using a new precursor called dimethyl aluminum isoprop oxide. So, we can either do this with water, which would be the traditional thermal ALD, or we can do this with oxygen plasma, which is plasma enhanced ALD. And in those two cases, we see that the plasma enhanced ALD actually has a significantly faster growth rate than the growth rate with thermal ALD. The other thing that plasma enhanced ALD allows us to do is often give us a larger larger ALD window, right. So, once again the ALD window is where we have this self-limiting growth. Typically in the middle of it there is a certain temperature window where the growth rate does not change. So, if you look at the ALD of this precursor with water, it does not really have a very nice ALD window. There is no region where it is very flat. You can maybe fudge it a little bit at these temperatures. However, once you do this with plasma enhanced ALD, you get a very nice and a very large deposition window, right, and that is one of the advantages. In fact, so much so that you actually get a deposition window where you get significant growth, almost the same growth rate as high temperature at very low temperatures. So, even at near room temperature, you can start getting depositions that you could not get before. So, not only do you get a wider window, but that wider window also allows you to do lower temperature depositions and higher deposition rate depositions. It also allows you to use much less reactive precursors. So, things like oxygen, nitrous oxide, carbon dioxide that are arguably safer and easier to handle. It allows you to deposit single component ALD, for example, metals. We can even deposit nitride. So, once again nitrides tend to be little less reactive, so hard to make using thermal ALD or require very high temperature. In the previous slide there was an example of using titanium nitride at 1000 degrees C, right, that is a very high temperature. But you can significantly reduce that temperature by just adding energy through plasma and doing things at much lower. The disadvantages is it is much less conformal. So, one of the advantages of thermal ALD was because everything is self-limiting, you do not care about the flow of gas, but now you have added plasma. So, now you have to worry about the density of plasma, its uniformity, etc., etc. So, that muddies the water a little bit and makes it less conformal in the extreme case. There is also more cost because you now have to design for plasma and RFs and DC power supplies, and it also tends to be less uniform precisely for the same reason. Now you have added plasma, so you have to worry about issues of plasma design that you did not have to before. What sort of characterizations do we do in order to analyze these films? So, this is a general list for both CVD and ALD. Typically people use SEM and TM to look at morphology, conformality, crystallinity, roughness, etc. AFM is used to look at morphology and surface roughness. XRD is very important. It allows you to look at crystallinity, orientation, what is the lattice parameter, is it lattice matched, not matched, what is the film stress. You can look at Raman. Raman tells you a lot whether if you have a substitutional impurity or not, what is your stress in the film, what are your lattice parameters. XPS tells you stoichiometry, very important. You are growing titanium dioxide, but is it really TiO2 or is it TiO2 plus X or 2 minus X? So, those are kind of studies can be done using XPS. And then if you want to look at doping, how much carbon contamination you have, how much oxygen contamination you have, you might want to do SIMS. With that, let me put a slide to summarize everything we have done in additive processing. So, we are going to move away from chemical vapor deposition and move to physical vapor deposition. But if we were to compare everything we have done till now, and we will compare it with using silicon dioxide, right. So, we can now do similar, we have looked at silicon dioxide as done by thermal processes, which is the native oxide growth. We have done it using a CVD approach where dichlorocyanine reacts with nitrous oxide. You can do it using TOS, which is MOCVD. You can get the same silicon dioxide by doing just silane reaction with oxygen, which is simple CVD. You can also do it with plasma enhanced CVD if you involve plasma. In these cases, what is happening is that the temperature from native oxide as you go towards PCVD, the temperature keeps reducing. And as the temperature keeps reducing, so does the quality. So, the highest quality films are formed at the highest temperature, lowest quality films are formed at the lowest temperature. Stoichiometry also tends to reduce. So, where you form very, very stoichiometric films at high temperature, not so stoichiometric films at low temperature. Depending upon what chemistry you use, you might have different impurities. This might have some chlorine, this might have some hydrogen, right? Step coverage tends to be better when things are temperature limited. So at high temperature, you tend to get good step coverage. When you are relying on things like plasma, you often do not get good step coverage. Thermal stability. So this is very stable, this is less stable, and you can sort of understand that you're just looking at the stoichiometry. Because it's off stoichiometry, it's a little more unhappy, and that makes it a little more unstable. In general, films that are grown that are higher quality tend to be more dense. So the native oxide is a very dense film, and as you go down to CVD deposited film, is slightly less dense. One exception is the PCVD case, where the density can sometimes be higher, and the reason for that is because you are bombarding the film with these ions, and they tend to compact the film and artificially enhance the density. Refractive index follows the same trend as density. In fact, refractive index is a very good proxy to understand what is happening to the density. So for dense films, you get good refractive indexes that are close to the bulk values, and for lower densities, you get poor refractive index that are lower. Dielectric strength again scales exactly the same way. More dense, higher quality films tend to have very high dielectric strength. Less dense, poor quality films tend to have low dielectric strength. The same strength can also be looked at in the resistance to chemical attack. So HF will etch all of these films, but at various rates. Thermal oxide will etch very slowly, PCVD will etch very fast. And finally, dielectric constant. The closer you are to a high quality film, the closer your value will be to the bulk value. Worse off your film, the worse your dielectric constant is going to be. Often because of these impurities, right? These silicon impurities, hydrogen impurities, oxygen impurities, often your dielectric constant is a little higher and off than the bulk value. So in general, if you were to summarize everything, depending on an application, you select a certain recipe, and that tells you at what temperature you can do that process. So there's always this give and take. You want lower temperature, you want more easier processing, you have to compromise on quality. You want higher quality films, you need the higher temperatures, you want you need the complicated equipment, and you need the complicated cleaning, you need the complicated recipes. Right? So you get what you pay for. Finally, a couple of slides on safety. This lecture series does not sort of include anything on safety, but CVD is one area where you have to be extremely careful. A lot of CVD precursors are extremely dangerous. They are toxic, pyrophoric, they can kill you, they will cause explosions, they will attack the stainless steel, they will attack the cylinders that they are contained in. And a lot of these things are both environmental dangers, but also personal life and safety dangers. So always treat precursors with extreme amounts of caution. If you are new to them, please talk to somebody who has experience in dealing with. Industry has a lot of standards on how to manage these types of gases, and we should follow them. Always have safeguards like alarms, sensors. Please have redundancy. Make things what we call idiot proof. Just saying that I will be careful is not a safety standard. A safety standard is assuming that somebody will make a mistake and then having something to prevent that mistake from blowing up. Okay. I'll actually end this lecture with an interesting, this is I think the second last slide of the lecture, where we'll end up with a slightly funny, in hindsight slightly funny report of a liquid nitrogen tank that exploded in a lab. Details can be found in this blog. Thankfully, nothing bad happened, which is why it's a funny story. But the thing I want to highlight is in this case, what actually exploded was a liquid nitrogen tank. Nitrogen is inert. As things go, liquid nitrogen tanks are one of the safest things you can have in the lab. Like all CVD precursors and all CVD equipment is actually more dangerous than this. And even then, the liquid nitrogen can cause so much damage. So just imagine what a CVD precursor can do, right? So let me just read it. So the cylinder had been standing at one end of a 20-inch and 40-inch laboratory. So what actually happened was that they had a liquid nitrogen tank. It was standing in the corner of a laboratory. All cylinders come with some safety valves, and some student or a postdoc somewhere along the way found one of the safety valves leaking. And instead of changing it, they just blocked it. So there was no safety release valve. So the system continued because it was used often. The pressure never built up to unsafe levels. But someday, the liquid nitrogen tank was not used for a long time. internally the liquid nitrogen evaporated, the pressure built up in the tank, and one night it exploded. So when it exploded, it was stored on the second floor of the chemistry building. It was on a tile covered with 4 to 6 inches thick concrete floor directly over a reinforced concrete beam. The explosion blew all the tiles off the floor for a 5 feet radius around the tank, turning the tile into quarter-sized pieces of shrapnel that embedded themselves into the walls and doors of the lab. Imagine what if somebody was there inside. The blast cracked the floor, but due to the presence of the supporting beam, this is the concrete beam underneath, which shattered, the floor held. Since the floor held, the force of the explosion was directed upward and propelled the cylinder, sans bottom, without the bottom, through the concrete ceiling of the lab into the mechanical room above. It struck 2 3-inch water mains, drove them and the electrical wiring above them into the concrete roof of the building, cracking it. The cylinder came to rest on the 3rd floor, leaving a neat 20-inch diameter hole in its wake. The entrance door and the wall of the lab were blown out into the hallway. All of the remaining walls of the lab were blown 4 to 8 inches off their foundations, and all of the windows, save for the one that was open, was blown out into the courtyard. So just imagine, like, if this happened not in the dead of the night where there is nobody in the lab, but in the day. So please exercise extreme caution with CVD. With that, just one slide on electroplating. So lately electroplating has become important, especially for depositing metals such as copper. The basic idea is fairly simple. You take your substrate, you put it in a electroplating solution, which is a salt of copper, and you put current, and depending upon whether it's cathode or anode, you will get a deposition of copper. Right, so this is fairly simple and known technique. People have started using this, even have proposed that they should use this even for silicon solar cells, because silicon solar cells have a lot of silver, and they are trying to replace that with copper. So I will not go into much more detail about electroplating. So this brings us to the end of the module of chemical vapor deposition as a whole. Next we shall talk about physical vapor deposition, which will be the final part of the larger module on additive processing. So see you then.